Hi everyone. Um, Welcome to my talk at the ArizeObserve conference today. Um, my name is James Lee, and I have pleasure to give a talk about this concept of DataOps for the modern computer vision stack. So, just a brief background of myself, so you can know familiar with the presenter. So my expertise really lies in enterprise MLOps and DataOps tooling. I'm currently driving content and partnership at SuperAI as part of the company go-to-market strategy. I'm also a writer. I write, blog posts that cover industry applications, emerging research team, and advice from luminaries in the field. And also a podcaster. I host a podcast that cover raw conversation with other practitioners and researchers to unpack some of the career lessons that they have learned along the way. It is called DataCast. Before all of this, I completed my graduate degree in computer science from RIT, where my research lies at the intersection of deep learning and recommended system, along with some of the cross-functional work on meta learning. In the past, I have built data science solution for fintech and e-commerce startup. I also used to freelance as a data journalist, having written more than 150 technical articles for a variety of startup blogs. And then besides all of that, my current interests are in venture capital and community-led growth, two areas that I think are quite relevant to the world of data and ML infrastructure startup. So here's a quick agenda of what we're going to go over today. First, I will define what is DataOps. Then I will explain why we need to bring DataOps into the domain of computer vision. Next, I will unpack some of the key DataOps principles. Then I will propose an ideal DataOps pipeline for the computer vision stack. Then I will examine some of the data challenges for computer vision teams. And then I'll close the talk with, potential future of the modern computer vision stack. Yeah, so let's dive right in and explore what is DataOps. And so to understand DataOps, you need to be familiar with the concept of DevOps. Essentially, DevOps is the transformation in the delivery capability of development and software teams, whereas DataOps focus on the transformation of intelligent system and analytic models built by data analysts and data engineers. So DevOps, as you can see in the slide, is the synergy of engineering, operations, and general development lifecycle, with the ideas to reduce the cost and time being spent on engineering powerhouse. Whereas DataOps add an additional layer of data, and basically different data teams work together at different levels to acquire data, transform data, model data, and obtain actionable insights. And I think just similar to how DevOps transform the way in which the software development lifecycle is work, DataOps also changing the primitive practices of handling data by implementing DevOps principle. And another representative of the Ops family is called MLOps, which merge the operations with the machine learning component. So it applies DevOps patterns to automate the lifecycle of ML models from their generation to deployment to retraining. And so both DataOps and MLOps can be viewed as an extension of the DevOps methodology in data science. So whereas DataOps cover the data journey from extraction to deployment of analytics products, it actually doesn't cover some of the solution for like model training and running models in production, and that is the part where MLOps steers initiatives. And so you might be wondering what has led to the rise of DataOps, right? So I think that there is really two main reasons. Number one is massive volumes of complex data. So any business nowadays that you can think of, works with large volumes of data coming from different sources in different formats. And in some of the large enterprise, the data landscape is very complex. Maybe you work with tens of thousands of data sources and format. Examples included, financial transaction, CRM data, and online reviews and comments. Secondly, to answer your business question, the data needs to be in a format that you can understand and use for analysis. That is why all the data that you gather must undergo a series of transformation, data analytics pipeline, and the data needs to be profiled, cleaned, transformed, and stored in a secure location to ensure data quality, data integrity, and relevance. And so for each of these processes mentioned above, you might be using different tools from data cataloging and data profiling to analytics and reporting tools, and that all led to, technology overload. Like for example, as you can see here in the slide, like there's so many tools that cover different part of the modern analytics stack, and that can easily lead to technology overload, right? And then finally, the people that are using the tools and technologies to work on your data are also diverse. Data engineers focus on data preparation and transformation. Data scientists worry about getting the right data for the algorithms, and data analysts care about building weekly reports and visualization. IT cares about maintaining data access protocols and guaranteeing data quality, data security, and data integrity. And finally, like the business manager are keen on finding whether the business is flourishing. And so bringing together diverse technologies, processes, and people with different mandates creates collaboration overhead and friction between teams. And that is why we need a DataOps framework in place. So this figure from the team of Workgrad and Flow provides a partial list of companies that are currently providing solution in the major areas that form the ecosystem of DataOps tooling. So at the bottom of the layer here, you see the infrastructure ops layer. And these are tools that monitor the data plane and initiates a response to an event or failure. Sitting on top of that is the data plane. So we have, tools that provide data coming from operation system, and this is the source system that supply data into the data warehouses, data lakes, and data lake houses. And the ETL and visualization layer also sit in this bucket. The DataOps stacks also includes a metadata layer that creates a map of organizational data flow, tracks the flow of the data, and enforces access and data quality. And then another layer consists of development tools used to manage complex processes. It may include multiple experiment and iteration, as well as collaboration that cuts across teams and units. And most of the MLOps and DevOps for data system reside in this layer. And sitting all the way on the top is the data product and services layer that includes tools used to track business KPIs and machine products and services. So for the next 3 slides, I'm going to argue for the case of bringing DataOps into the domain of computer vision. First reason is that in most real-world machine learning, the data is more important than the models. And this contrasts with academic machine learning, which emphasize the modeling component rather than rethinking the data paradigm. There are currently so many data-related low-hanging fruits that we're missing. And whenever a model performance is bad, we should not only resort to investigating the model architecture and tuning hyperparameters, we're really should think about like how to identify the root cause of bad performance in the data. And I think that DataOps as a discipline can help you visualize, curate, and label only the data points that are A, worth being labeled, and B, yield the most value with respect to a given task. The second reason is that preparing massive volume of unstructured data in computer vision pose a variety of challenges, right? Dealing with the unpredictable nature of images and videos, managing the labeling workforce, allocating sufficient labeling budget, addressing data privacy, and more. Before carrying on with the modeling component, the labeled data needs to be audited for correctness and quality. And this can only be done via rigorous data processing, data transformation, data augmentation, data visualization, and label validation to see if the data can serve as part of the training set. So DataOps can help teams to spend time on gathering high-value data and creating valuable data sets. And especially with, best practices like CI/CD, for instance, the data engineers can automate the data preparation workflow more seamlessly. And the final reason is that building computer vision application is iterative. So as you see here in this slide is a very nice diagram given by a talk by Taiwo Punkas that described the two loops of building algorithmic products, which included the algorithm development loop and then the product development loop. So the algorithm development loop included 3 separate steps. You first build the algorithms using ML frameworks. You measure your algorithms against your evaluation set, right, using annotation spec and other testing in-house tooling. Then you learn from failure cases using error analysis and manual review tooling. Separated from that loop is the product development loop, which also entails 3 different steps. You first build your products using microservice and infrastructure frameworks, and then you measure your products in production using monitoring and logging tools. And then finally, you learn from some of the failure cases using dashboard and analysis of live performance data. And so DataOps, can speed up the iteration of these 2 loops, which work together in at least 2 ways. You can, go from step 3 here to step 4. Basically, after building the algorithms, the scientists can provide those algorithms to the engineers to incorporate them into the computation products. Another way that these 2 loops work together is go from step 6 down to step 1 here, where, after learning from some of the use case failures, the engineers can instruct the scientists to sample and annotate only some of the failure cases, right? And then those failure cases will be incorporated into the new training set for the next iteration of the algorithm development loop. And so given that the practice of DataOps is fundamental to how data moves across the stack, it is crucial to understand some of the core principles of DataOps. And so there are 6 principles for all of the data analytics projects, which I will explain in detail as follows. And for each of them, I will examine how they can be adapted for computer vision projects. First principle is to implement best practices for development. So in the data domain, data engineers, data analysts, and data scientists come from different sorts of background, but the key common ground here is that they need to do a lot with code, right? So it is imperative for them to follow software development lifecycle guidelines, right? So in practice, these guidelines included version control, code reviews, unit testing, artifacts management, release automation, and infrastructure as code. So applying these software development best practices for computer vision is quite straightforward. To get started, I recommend following this document by Google called Rules of ML, and then another checklist coming from this website called SC4ML. And this list gathers a set of engineering best practices for developing software system with machine learning components. The second principle is to automate and orchestrate all data flows from initial source to final deployment. So you want to automate your deployment with a CI/CD pipeline and then discourage any kind of manual data wrangling. The best way to go about this is to run your data flows using an orchestrator for tasks such as backfilling, scheduling, and gathering pipeline metrics. And I put here on the slide some of the well-known open source orchestration tools, including Apache Airflow, Dagster, and Prefect. So applying CI/CD for computer vision is also quite straightforward. A great resource to get started is this article by ThoughtWorks that essentially explain how to bring continuous delivery principles and practices to ML applications. The third principle is to test data quality in all stages of the data lifecycle. So in practice, you definitely want to, test your data at the source by running data unit tests, right? And then depending on the data source that your pipeline is connected to, you can write extra, extra different type of tests like schema tests, SQL tests, or streaming tests. Then you want to validate the data as it goes through different stage of the data flow, right? Maybe you go from the source to the staging environment. Maybe it goes undergoes transformation, and maybe the data get promoted to production, and definitely when the data goes into the data warehouse. Next, you want to capture and publish some of the metrics across some of the stages that I just mentioned. And finally, you want to reuse your test tools for your following projects by building a common testing frameworks standardized across your data team. A pretty well-known open source option for data quality testing is called Great Expectation. Now, for computer vision, continuous testing is trickier because you have to think about accuracy across your overall data set, and that includes things like raw data distribution on top of the label consistency. You have to answer a question like, does the work of all of your labelers look the same? Is labeling consistently accurate across your data set? And given the fact that there's the human in the loop component, right? Building a common testing framework for label quality is definitely not an easy task. So the third principle is to monitor quality and performance metrics across the data flows. And also another term for this is to improve your observability practices. And the first step here is to define your data quality metrics, which can be broken down into technical metrics, functional metrics, and performance metrics. And the second step is to visualize these metrics to appropriate data stakeholders so that they can take meaningful actions using meaningful alerts. So, you might ask, what does observability look like for computer vision, right? So I think that it could be a combination of data observability and model, observability. So a team over at Monte Carlo defines the 5 pillars of data observability to be freshness, distribution, volume, schema, and lineage. And in the context of computer vision, I think this translates into roughly this question, like how up-to-date the labels are updated, how the label are distributed within an image, how big the number of images is, how the labels are visualized and formatted, and then how the images are versioned. The Arize team, wonderful organizer of this conference, defines model observability as the process of collecting model evaluation in training, validation, and production environments, and then tying those evaluation with analytics to allow practitioners to connect these points to solve the ML engineering problems. And I think this translates directly into the computer vision workflow, where the output prediction from one model serve as the input training data for the next model iteration. Going further, the team at Y Labs proposed the anatomy of an enterprise AI observability platform, which included key capabilities such as telemetry collection, time series database, a debugging engine, an anomaly detection engine, and a visualization layer. Okay. The fifth principle here is to build a common data and metadata model. So most organizations face a significant challenge because the data can come from different sources and everybody look at the system from different angles. So borrowing from the domain-driven design concept in software engineering, you definitely want to identify similar terminologies across different areas and then share them across different teams, right? And tools like dbt, for instance, can enable you to combine different data sources and put them into a common data warehouse. A more enterprise focus is to invest in a data catalog to share data knowledge more broadly across the data organization. And with a data catalog, each data owner knows exactly what he or she is provided with, right? And some of the well-known open source tools in this domain is Amazon by Lyft, Data Hub by LinkedIn, and Marquez by WeWork. So for computer vision, this really means creating a repository of all of your image and video data from different sources, including some of the details on the structure, quality, definition, and usage. And ideally, you can allow your users to access the metadata along the data itself. And for images and video, the metadata here comes in the form of JSON objects. And one thing that is still hard, in my opinion, is version control for unstructured data. And a solution like Pachyderm is a promising option that is currently on my horizon. And then furthermore, a sophisticated solution that can provide a graphical representation of the data assets lineage can simplify future data governance and compliance concern. The sixth principle is to empower collaboration among data stakeholders. So there are different ways to structure your data teams, but I think the best approach is to embed the data thinking into every functional team. It is similar to how to the Agile principle, where you want to build a cross-functional team with no division between key function. This team can define important metrics and KPI together and craft shared objectives with the business goals. And furthermore, to remove potential bottlenecks for data usage, you want to set up self-service data monitoring and democratize access to the data. So while building computer vision application, I believe that an ideal DataOps team should be composed of the 4 core functions as outlined here in the slide. So the data labeling manager often work with in-house or offshore labeling teams to help scale the throughput of data labeling. They define labeling instruction, inspect the work of the labeling team, then decide how to handle some of the more complex or ambiguous scenarios. The data engineers are responsible for designing, building, and maintaining datasets that can be leveraged in ML projects. As such, they closely work with ML engineers. The data curators are expert in their respective domains, visualizing and manipulating ML datasets. The knowledge of the business goals and the ML capabilities can inform how best to prioritize data curation to improve the ML system. And then the head of DataOps provides strategic oversight to the DataOps team. The goal is to create an environment that allows all different parties to access the data that they need painlessly, build the skills of the business to draw meaningful insights from the data, and then to ensure data governance. And they also act as a bridge between the DataOps team and other functional units, serving as a visionary and a technical lead. So I think that collaboration process between all of these different roles is still ad hoc at most organizations, and there's definitely room for tooling that can make this process more efficient. And so, as I alluded throughout the slide, right, DataOps for vision really means building a high quality training data set. And this entails asking questions like, what data, where to find that data, how much data, where to validate the data, what defines data quality, where to store the data, and how to organize that data, right? So the next slide is my attempt to propose an ideal DataOps pipeline for the modern computer vision stack. And this is definitely a work in progress, and that I conceptualize via a lot of conversation and reading across different channels. And if you have any feedback or commentary on it, feel free to reach out and channels with me later on. But yeah, so the first block is the data acquisition block, right? So when we talk about data acquisition, we tend to think about data collection, and basically there are both the physical and the operational consideration with this, like ranging from where to collect the data to like how much to collect initially. But besides data collection, we also have synthetic data generation as another option, and there are so many use cases using synthetic data, like ranging from facial recognition to e-commerce to autonomous driving. However, getting this synthetic data requires managing data and compute. And furthermore, synthetic data is not realistic for unique use cases, and there is a lack of fundamental research on the impact of model training. Then finally, the third approach is known as data scavenging, where you basically can scrape the internet or use open source data set, like from Cargo or public academic benchmark, right? Second block is data labeling. This is an industry of its own because we have to answer so many questions, like who should label the data, how should the data be labeled, and what data should be labeled. So indeed, like getting the labeling step right is extremely complicated because it is error prone, slow, expensive, and often impractical. Efficient labeling operation could require a vetted process, qualified personnel, high performance tools, its own life cycle, a versioning system, and a validation process. The third block is data debugging, which entails writing expectation tests to address the data preprocessing and storage system. Essentially, they are the unit tests for your data, and these tests are designed to catch data quality issues and bad data before they make their way into the DataOps pipeline. The fourth block is data augmentation. This is a scientific process where you can manipulate the data via flipping, rotation, gestation, grayscaling, etc. However, scaling data augmentation to bigger data sets, negating memorization, and handling some of the corner cases are still some of the fundamental issue here. The fifth block is data transformation, and this actually includes 3 different steps. So data formatting is a small slide of the whole data engineering task that interface with data warehouse, data lakes, and data pipeline. Feature engineering, so this includes concepts like feature store, management of correlation, management of missing record, and going from feature selection to embeddings. And then data fusion. This last step means fusing data from different modalities, different sensors, and different timelines. Data curation is a very critical block that I think is quite underrated because it bridges the gap between the DataOps pipeline and the MLOps pipeline. So the fundamental belief here is that you need to be picky about choosing what data to use for your ML lifecycle development, right? So actually, first you need to catalog the data, and then you also need to structure the data in a very methodological way. You can sort the data by use cases, or you can make the data searchable using predefined tags. You can even cluster the data using specific embeddings and metadata. After cataloging and structuring, you only want to select the data that is most useful, for your ML system design, right? And useful here means like the data that that for sure that could improve your model performance, right? And just to kind of close the feedback loop here, we have a final block, failures and edge case detection. And here that entails activities like drip detection, performance matrix monitoring, and data observability. So the idea is you want to detect some of the cases where your model underperform, and then basically acquire more of those edge cases and use them as new data points for the next iteration of your computer vision workflow. So with that, I want to kind of go over some of the key challenges that any vision teams have to deal with, just to kind of like go deeper in some of the points that I mentioned in the previous slide. Challenge number 1 is to curate high quality data points. So in the context of vision, like data curation is massively underrated because currently there is no streamlined method to understand what kind of data has been collected and created into a well-balanced, high-quality data sets, right? And unfortunately, like data curation remains like the most time-consuming and least enjoyable work of data scientists and data engineers, because the data curation tasks often require substantial domain knowledge, and existing techniques cannot keep up with the 4 V's of big data: volume, velocity, variety, and veracity. And furthermore, these solutions are quite narrow because they primarily learn from the correlations being present in the training data. And therefore, it's pretty likely that they not be sufficient to encode some of the domain knowledge in general, right? And I think that functional DataOps platform for computer vision should have data curation capabilities that enable data and ML engineers to understand the collected data, identify important subsets and edge cases, and curate custom training set to put back into the models. And more specifically, like this platform should be able to visualize massive data set, discover and retrieve data with ease, curate diverse scenarios, and integrate seamlessly with existing workflows and tools. Second challenge is to label and audit data at massive scale. So you know that training vision models require a constant fit of large and accurately labeled dataset. However, this typically requires a considerable time and capital commitment, especially since most of the labeling and quality assurance is done manually by humans. So I work at SuperAI, and data labeling is really our bread and butter. And based on our conversation with a lot of practitioners in the past couple of years, like data labeling and auditing are still the major bottlenecks within the data preparation pipeline for computer vision system. And interestingly enough, like based on our conversation, like this bottleneck applies to both teams that just started a vision projects, as well as some of the more mature teams with models already in production. So, like for instance, like for some of the key companies in the early stage of the development, ML development, and they want to utilize AI somehow, they actually do not have any models being pre-trained on some of the niche or domain-specific data set that is unique to their use cases. And for some of the more mature teams with models already in production, they want to focus more on improving their model accuracy, and therefore they need to identify like where the model is failing and then manually prepare data sets to address those edge cases. So I think that an effective DataOps platform for vision must definitely address these two expensive steps of labeling the data and then auditing the labels, right? And at SuperAI, we're trying to build a product that can help our clients to immediately identify the hard labels, build in active learning workflows for auditing, and then deliver data sets in a matter of days instead of months. And the third challenge is to account for data drips. So computer vision system suffer from a major limitation that constrain the accuracy on real-world visual data captured at a specific moment in the past, because they have a built-in assumption that the mapping function of input data used to predict the output data is assumed to be static. However, in practice, like the visual data can drift over time because it comes from a dynamic and time-evolving distribution. And this phenomenon is known as data drift. And basically, like the prediction made by a model that was trained on a historical data may no longer be valid, and therefore the model performance will begin to decrease over time. And especially as more ML applications move towards streaming data, the potential for model failure due to data drift can exacerbate. And there's so many different causes of data drift, like upstream process change, data quality issue, natural drift in the data, and covariance shift as well. So I think that a robust DataOps platform for vision should be able to detect the data drift and then raise alert, analyze where and why drift happens, and also adapt to drift and have improved model performance in general. So I will to conclude my talk by giving some ideas on how the future of the modern computer vision stack can look like. I think it will follow the footstep of the modern data stack, which is a collection of cloud-native tools centered around a cloud data warehouse and together comprise a data platform. And so the benefits of adopting a modern data stack are many. you have ease of use. So basically, every tool is built for the data warehouse. So this minimizes integration pains and silo data platform that requires a lot of effort spent shifting data around. There's also wide adoption. So, SQL is the lingua franca that creates a common foundation to work with data across discipline. There's automation because, it reduces the time for practitioners to operationalize the data workflows. And then there's also cost, right? Because in the cloud, you pay for what you use, nothing more. And that can help teams to get more done in less time with fewer resources. As the modern data stack continues to grow and evolve, many new technologies and vendors are entering the conversation. You see here in the slide is a diagram created by the team over at Continua that entails some of the current main functional areas of the modern data stack. So you have cloud data warehouse, data integration, event tracking, transformation, AI, ML, BI, reverse ETL, and then governance as well. And I think we're seeing a similar, evolution of the modern ML stack, right? Of which, vision is definitely a subset of it. And so I work at SuperAI, and we have the pleasure to be a member of the AI Infrastructure Alliance, which is an organization that is dedicated to bringing together the essential building blocks for AI applications up today and tomorrow. So right now, we are seeing the evolution of canonical stack for machine learning is coming together through the efforts of many different people, projects, and organizations. And that's why the Alliance was created to act as a focal point that brings together many different groups in one place. And the members of the Alliance try to bring clarity to, this quickly developing field of MLOps and ML infrastructure by establishing clean APIs, integration points, and open standard for how different components of a complete enterprise machine learning stack can and should interoperate. And so, and the whole goal is to, have, organization make better decision about the tools that they use to deploy into the enterprise ML stack, right? And this diagram you see here is an early draft of some of the emerging patterns that we have seen across the different, like now more than 100 members of the Alliance. Then finally, I want to conclude my talk with this diagram that broadcasts some of the types of ML infrastructure companies divided based on their value added to the life cycle. And this wonderful diagram came from a blog post by Lishmary Braswell, who's an investor at the Founders Fund. Basically, there are 5 different categories that she categorized: making core workflows better, faster, and cheaper, optimizing communication, improving production model reliability, augmenting data programmatically, and removing the need of specialized ML engineers. And this, different startup have covered, either one or more than one of these categories. And these categories are meant to deal with existing ways of doing machine learning, like deep learning, gradient boosting, etc. But if there are some of the more nascent methods that in research that take up, like maybe reinforcement learning, maybe self-supervised learning, for instance, then the infrastructure we need to adapt to, satisfy some of the new requirement from those new research domain, right? So yeah, highly recommend giving that a read. And that's the end of my talk. I hope you enjoyed. Appreciate you spend your attention and time watching it. And if you want to, trade notes on me on how the modern ML stack going to evolve in upcoming years, also feel free to DM me on Twitter, and we can continue conversation from there. If you interested in learning about some of the work that we're doing at SuperAI, my email here is on the slide. And if you want to check out some of my other work related to writing, podcasting, and community development, then yeah, check out my website, and would love to get you involved. Thanks everyone.